Okay, we are all set now. Good. Okay, so as I was saying, we will start today's discussion with a chapter that we skipped initially, the one on the buffer manager, which remember was one of the components, one of the modules that we have seen together in the modular architecture of a relational database management system. So this is discussed in the chapter 9 of the Cowbook third edition. Okay, so here we are, let's say, in the modular architecture of a relational database management system, and what remains to be clarified in this stack of modules is the buffer manager. And then we will see somewhat in parallel or on the side, let's say, with respect to this architecture, we will have two other very important components, modules responsible for transactions and recovery from crashes. And later on today, we will start as well the discussion on transaction management. So we are here and zooming a bit, let's say, on the layers responsible for dealing with pages of data, getting them from disk into main memory and then accessing, managing them. This represents, let's say, the first three layers of the modular architectures, the ones illustrated here, the disk space manager, the buffer manager, and the files and index manager. And of course, we have the database underneath, let's say. And the buffer manager, the module that will be the topic of our discussion now, is of course about managing some kind of buffer zone, a memory zone in main memory close to the CPU, which is, by now you should know this of course, which is in general significantly smaller than the disk space, the available disk space, and significantly smaller than the data itself. And this is illustrated here by this blue area that represents, let's say, the buffer manager. And in this blue area, the memory space that is managed by the buffer manager, we have, let's say, frames, slots in which we can place pages of data, pages that we get from disk. So we see here a few pages of data on disk, and we see the frames. You can think about the frames as some kind of parking slots where we can park, we can place pages. They're memory zones of the same size, let's say, as the blocks of data, the pages of data. And this is done by the buffer manager, uh, while, let's say, maintaining somehow an illusion of addressing and modifying disk pages in memory. And this illusion, of course, is maintained for the files and the index manager, the module above. And this illusion of addressing and modifying disk pages directly by working with them in main memory is, let's say, the main role of the buffer manager. This, of course, means transferring these pages to and from disk into main memory whenever necessary, while also paying attention, let's say, to many constraints that must be met, many conditions that must be met. And we will, of course, clarify all that throughout our discussion. And of course, this illusion is hard to maintain since, once again, we have much fewer main memory space than disk space and data. So this is why the work of the buffer manager is very important and very critical, let's say, in the functioning of the relational database management system. So for now, let's say abstracting away from everything the buffer manager does internally, for the modules above, its role will be to answer a very simple API, read page, write page. This is how this module will be used by the modules above. And this is the kind of API, of course, that we will also find for the dialog that the buffer manager has with the disk space manager, read page, write page as well. Okay, and let's get now into more details about, let's say, the internal aspects, internal details of the buffer manager. And let's start, of course, with the main ideas, principles that drive, let's say, the policy of the buffer manager, the one for getting pages from disk to the buffer zone and vice versa. So let's start simple, and let's say that the first page must be read, is requested by the modules above, read page 1. For now, obviously, this page, since let's say we start with a buffer zone that is completely empty, this page is not in main memory already, so the buffer manager has to forward this request to the disk space manager. Read page 1 from disk. The page 1 is read and is transferred to main memory. Then let's say we get another request for page 2, and the same happens here. The buffer manager will forward this request to the disk space manager. The page is transferred. And so we will often, let's say, in this kind of process, we'll often talk about, let's say, a primary copy of a page, which is the one on disk. So for instance, here, page 2 has 2 copies, the primary one, which is on disk, and a secondary copy in main memory, the one, let's say, currently under use. And the same, of course, holds for page 1. So primary copy and secondary copy. Okay, let's continue. Now, yes, so a second request for page 2 arrived, and now we do have page 2 in main memory, and this is quite helpful because we no longer have to forward this request to the disk space manager, and we no longer have to pay the cost of an access to disk. So the page is already here, and we can serve it, let's say, to the corresponding request. Requesting page 3, of course, means getting another page from disk. And all this being said, now a first quick quiz for you. B+3 algorithms make read requests from the disk space manager or the buffer manager. And each frame in the buffer pool is the size of a disk page, may contain a cache of an arbitrary disk page, is stored in main memory, or all of the above. What do you think for the first question? Is it A or B? Good, everybody. Well, not everybody, but there seems to be a majority for A. And of course, the answer, I don't have the answer, unfortunately, but the answer is B, of course. All the requests for pages go through the buffer manager. And regarding the second question, each frame in the buffer pool is the size of a disk page. So once again, the right answer here is B, the buffer manager. Each frame in the buffer pool is the size of a disk page, may contain a cache of an arbitrary disk page, is stored in main memory, all of the above. Of course, all of the above. Each frame can accommodate a disk page and may contain at any moment an arbitrary disk page, and is of course part of the main memory. Okay, all this so far is easy, too easy in a way we could even say, but of course when dealing with this getting of pages to and from disk, we have to deal not only with let's say the read aspect, but also with writes, with saving pages to disk. We have many operations, of course, that will modify secondary copies, buffer copies of pages, and you will see that we will call such copies that have been modified dirty pages, pages that have been written upon, and we will have to deal with also with page replacement in most situations, and we have already said that quite a few times today. Since the buffer is much smaller than the data itself, most of the time the buffer will be already full. Um, when a new read request arrives. And in order to bring the requested page into main memory, we have to make space for it. We have to send out, to kick out some page out of main memory to disk in order to make a slot, of course, available for the newly requested page. This is what page replacement is about, and you can imagine once again that most of the time uh, we will have to set up policies that will try to avoid as much as possible situations in which each request of a page means sending out an already existing page from the main memory to disk in order to make space for the newly requested page. So let's start now the discussion, first of all, with dirty pages, pages whose buffer copy has been modified, pages whose secondary copy has been modified. So this is illustrated here. And first of all, let's see what we need, let's say, as main ingredients for handling dirty pages. We need, first of all, let's say, an indicator, and this will be the so-called dirty bit, an indicator that a page has been modified by some operations over that data. In certain cases, of course, pages may be modified. In others, they may just be read and therefore not modified, and therefore we need such an indicator. And with this dirty bit on, valued 1, obviously, whenever, let's say, a page must be replaced, we write it back to disk, since the copy on disk, the primary copy on disk, is now, let's say, stale, no longer synchronized with respect to the modifications that have been done in main memory. So for now, let's just assume that the page is written back to disk only when two conditions are met. It must be replaced. It has been chosen, let's say, as the one to be replaced by a newly requested page that must be brought from disk to main memory. And second condition, it is dirty. So it must be replaced and it is dirty. Only in this situation, we will write it back to disk. And again, this also obviously means that if a page must be replaced but it is not dirty, we will simply forget about it. We will simply throw it away. We don't have to write it back to disk because the primary copy that we have on disk is already is exactly the same as the one we are replacing in main memory. There is no need to write anything back to disk, so we just throw it away. Okay, so now let's talk about page replacement, of course, which is, let's say, the missing component in this construction. So let's say we are in the following situation. We have a buffer zone that is full. As you can see here, we have 6 slots and all occupied by a page. We have the copies of pages from 1 to 6. And a new request arrives for page 7. in order to bring a copy of 7 in main memory into the buffer zone, we need, of course, to empty first a slot for it. Which one? Well, it really depends, I would say, on two things. Um, which pages among 1 to 6 are still in use, because if a page is in use, it's definitely not a good idea to send it back to disk. Being in use means that immediately after we may have to bring it back. So we should definitely not kick out a page that is still in use, since very soon we will need to bring it back. And also, if there are several frames or pages to be considered for replacement, how do we choose if we have several choices here? Do we follow some rules or a policy, or do we just, let's say, pick randomly? Do we just toss a coin? This is what we will see next. And for the first aspect, first of all, since we need to know if a page is still in use, another indicator will be necessary here, the so-called pin count, which will simply indicate how many different operations are still using that page. So it will no longer, it will not be, let's say, a binary indicator, 0, 1, but it will be an integer value, a pin count, indicating how many different operations are still using that page. If the pin count, of course, is 0, we have a page that is no longer in use. If it is 3, we have 3 different operations that are currently using that page. Let's say 3 different queries that are looking at the data from that page. Okay, so I think you should have got the idea here. And so for the second aspect, the policy, the replacement policy, we will see throughout our discussion today several possible policies, each of them with advantages, let's say, and disadvantages. Okay, then besides the questions that we'll clarify together, the ones from the previous slide, there are more advanced questions that have to do with concurrent operations on a page. Think about, for instance, three users querying the same data on the same page at the same time. We'll talk about concurrency control starting today, later on, and we will see the implications of such, let's say, concurrent operations and how they impact also the buffer manager when we talk about concurrency control. And second important aspect, crashes that may intervene, let's say, before the buffer manager wrote back to disk a dirty page. So a crash most often means that everything that was in main memory at the moment of the crash is lost. And therefore, recent modifications on a page, on a dirty page, that were not yet saved to the disk copy of that page may be lost. And we will see how this is handled by the crash manager, and again, how this may impact the buffer manager as well. So we'll talk about concurrency control and crash recovery starting today later on. And we will see that these two modules in particular interact in non-trivial ways with the buffer manager as well. Okay, so let's now further start clarifying, let's say, the page replacement mechanisms. I would say with attention to this aspect, in use or not in use. In use, not in use pages, and the replacement policy. Let's say this is our example, our buffer zone right now, so filled with pages from 1 to 6. And let's make the discussion a bit more precise here. This memory space is in fact a rather, let's say, contiguous range of memory in RAM. And let's say we have all the information about it in this tabular format, in this little matrix, let's say, a kind of an index more precisely, where for each frame or slot, the page ID of the page currently occupying that slot is given, and then we have the dirty bit information and the page count of that occupying page. So this is, let's say, what we will keep track of in this index. And for instance, the corresponding index to the image that we saw before with the buffer zone full filled with pages from 1 to 6 may be this one. So we have in frame 1, page 1, in frame 4, page 6, and so on. You see that some pages are dirty while others are not. And you also see the pin count. Some pages are currently in use. 2 pages are currently in use. Page 2 from frame 2 and page 6 from frame 4. Okay, and so how we keep track of this information, we keep an in-memory index, a hash table on page ID, because in this way we can very easily, by lookup, with lookup by page ID, we can easily tell whether the page is in main memory or not. Okay, so this will be a running example. And so this matrix corresponds now to this buffer zone indicated here. So you can see the pin count, and you can also see which page there is only one, page 2 are dirty. Okay, so let's continue with this example. And when a page is requested, the logic that will be followed is rather, let's say, straightforward. If the requested page is not in main memory, in the pool of frames, we will have to choose, and assuming, let's say, that the buffer zone is full, of course, which most of the time always will be the case, we'll have to choose an unpinned frame for replacement. Unpinned, obviously, because this means a page that is not currently in use. If that frame is dirty, so if the page occupying that frame has been modified by some operations before, we have to write, of course, that page to disk and then mark it as clean, no longer dirty. And then we read the requested page into the frame. We are not yet done. We have to pin the page in order to indicate that it is currently in use. Some process, some operation requested that page and therefore is using that page, and we return its address. We will tell, for instance, the index manager that requested that page, your page is now in slot 5 of the buffer zone, for instance. And if requests can be predicted, of course, for instance, if we do sequential scans and we know that after page 1 we'll need page 2, and after page 2 we'll need page 3, and so on, obviously we should try to prefetch several pages at a time in order to reduce input-output operation costs. Okay, so let's see this on our example. Let's say that in the current context, page 2 is the one to be replaced. We'll see what policy may lead to such a decision, let's say. So we have to deal with a request for page 7, the buffer zone is full, and let's say we picked page 2 for replacement. So we have to save it to disk because that page was dirty, and then we bring page 7 in instead of page 2, and we pin it, we mark the fact that now this page is used by one operation, the one that requested page 7. And then we send a pointer to the requesting module, for instance, the index manager, saying, well, your page is at, let's say, address 123 or slot 123 in the buffer zone. Okay, so after the requester finishes, so after, for instance, the index manager finished working with page 7, that requester must indicate whether the page was modified via the dirty bit and unpin it. That's very important. And so there are a few questions that we have to consider here. Why is it in particular that the requester unpins and not the buffer manager directly? Simply because it is, of course, the requester that is supposed to know when a page is no longer in use. Remember that unpinning means declaring that the page is no longer in use by one operation. So unpin basically amounts uh, to removing one from the count, indicating how many operations are using a page. So unpin means decrement the count. What happens if, for instance, the requester does not unpin as soon as possible? Well, we have a page that is still indicated as currently in use, even if this is not the case. And we may end up in situations in which all the pages in the buffer zone seem to be currently in use, and therefore there's nothing to be replaced, and therefore we can no longer uh, deal with new requests for pages. And that, of course, would be quite problematic. So this is why it's important for requesters of pages to unpin the pages they use immediately after they stopped their work with those pages. So finally, let's say now we will get to the replacement policy and how, let's say, we should uh, we should decide by which rules or by which constraints which page should be replaced when a new request arrives. And obviously, the logic here will be to minimize the probability of so-called cache misses. A cache miss is simply a situation in which a page that is requested is not in main memory. And so we'll try to minimize the probability of cache misses, the number of times a page that is requested by some process, by some module, is not already in the buffer zone. Okay, so other details here. So obviously, a page in the pool may be requested many times, and this is why the pin count will keep track of not only the fact that the page is in use, but by how many operations at any given moment that page may be used. And so to pin a page, for instance, if a new operation requests a page, we'll simply increment, and that page is already in main memory, we'll simply increment the pin count. And once again, the pin count plays a major role for replacement because a candidate for replacement is only a page is a candidate for replacement if and only if the pin count is 0, if and only if the page is no longer marked as currently in use by one or several operations. We will also see that the concurrency control and the recovery manager may also require, let's say, additional input-output operations upon replacement in order to allow mechanisms for crash recovery, for instance. We'll talk about that next week. For instance, the write-ahead or WAL protocol requires such additional input-output operations upon replacing a page with another one in the buffer zone. Okay, so now if a buffer is full, what page should be replaced? And this is the role of the replacement policy. And as I was saying before, we'll discuss several such policies, and we'll see what may be the advantages and the disadvantages of each of them. So let's continue the discussion with the replacement policy. So remember that the goal of any replacement policy is to minimize the probability of a cache miss, to minimize the probability that a page that is requested is not already in main memory. And there are, I would say, two rather popular such replacement policies, which basically look at the timestamp when a page was last used. And depending on that, we have a policy that will select for replacement the least recently used page, and another one that will select for replacement the most recently used page. And obviously, you can immediately see that these two policies are rather contradicting each other in a way. One picks depending on one picks the page with the, let's say, the smallest timestamp value, or the other one picks the page with the highest timestamp value, the most recently used page. And we'll see that these choices, least recently or most recently, may impact significantly the performance of the buffer in terms of cache misses, in terms of this probability of having already in main memory a page that is being requested. Depending, of course, on the patterns of access to data. In some, let's say, scenarios, LRU may be a good idea, while in others, MRU will be a good idea. So we will discuss, of course, this in the rest of our discussion, depending on access patterns, which policy may be preferable. Okay, so let's look now, first of all, at least recently used. And I would say that this policy has two main advantages. First of all, it is intuitive, let's say simple to comprehend, rather natural, and also simple conceptually to enforce, conceptually. I think it sounds rather natural to say that we should replace the page that was least recently used. So most likely that page will not be requested immediately after, for instance. Most likely that page has been used at some point before, and it's no longer likely that it will be used in the near future. So it's a policy that is also quite effective when we have, let's say, certain pages that are much more popular than others. For instance, let's take an example of a Twitter account of a famous, let's say, artist, and that account and the database page holding that account might be accessed, of course, much more frequently than, let's say, the average Twitter account. In such a situation, the least recently used policy is a good policy. It's good for, let's say, temporal locality. For pages that may be accessed much more frequently than others within a short time lapse. In situations when we have such pages which are much, let's say, hotter than others, they may be accessed much more frequently than others within some short time lapse. On the downside, enforcing least recently used may be a bit costly. It sounds conceptually easy, of course. We just need to find, for instance, a mean on the column of the timestamps on the column that indicates when a page was last used. But when we have, of course, tens of thousands of pages and very little time in order to decide upon this replacement step, least recently used may become a bottleneck. And solutions to this problem, a solution, let's say, to this issue is something that is a bit less costly and unavoidably, let's say, a bit less precise, but goes more or less, follows more or less the same logic of least recently used on whether, let's say, a page is more or less among the ones that have been least recently used. And we will see such a policy next. It is called the clock policy. And we can see it, let's say, as a simplification of least recently used, which will go as follows. So once again, the least recently used policy needs to find min, a minimal value on the last used attribute. For instance, here, the page that should be replaced, the frame that should be chosen for replacement is the one holding currently page 6 because it has been last used at timestamp 11. And so let's see now the clock policy. So findings, conceptually this is easy once again, but finding such a minimal value fast when we have tens of thousands of frames, for instance, may be a bit too costly. So let's now talk about the clock policy as well. So Here is the current illustration. So let's say this is the buffer manager state, pages 1 to 6. Pages 2 and 6 are currently under use, are pinned, and page 2 is dirty as well. And with the clock policy, uh, logically, let's say pages will be organized um, in some kind of circular fashion as the time steps of a clock, the time moments, let's say, of a clock, and they can be visited in round robin fashion, clockwise, one at a time, by a clock hand. A clock hand that will basically indicate the next page to consider for replacement. And so at any given moment, the clock hand points to the next page to be considered for replacement. Besides that, there is a bit of meta information that we carry, the pin count and the dirty bit that we have, of course, introduced before. And we now have an additional, let's say, meta information, the reference bit, whose role is to, it's a binary information, and it's a binary way, let's say, to indicate whether a page has been used recently or not. So this is, let's say, uh, how we more or less follow the same logic as least recently used, but in with a procedure that will allow us to decide upon replacement much more easily than least recently used. So we no longer have timestamps. They are replaced by this reference bit, which once again will indicate whether a page has been recently used or not. And now it will be just a binary indication, no longer a timestamp. So let's see how this works. This is our state, and we'll see this next in clockwise, let's say, fashion. So we have the frames, of course, we have the pages occupying the frames. It so happens that here the page ID occupying each frame is equal to the frame ID, but of course this is just a coincidence. We have the dirty bit information, the pin count, and the reference bit here. And the clock hand, let's say, is equal to 1, so the clock hand is let's say, pointing to frame number 1. Now, a new request arrives for page 7, which of course is not in the buffer. So we have a cache miss. Initially, the clock hand, as indicated before, points to frame 1, which is occupied by page 1, which is pinned. So definitely not a good candidate for replacement. Therefore, the clock hand needs to move to the next frame. So this is indicated here. And the same goes, of course, for page 2. It is also pinned. It is also currently in use. So we will skip it as well. And now we arrive at page 3, which is at slot 3, which is occupied by page 3, that is not pinned, but whose reference bit is on. As you can see here, this is the reference bit. And because of it, assuming that, once again, considering that this is an indication that page 3 has been recently used, we will continue. We will not decide to pick page 3 as the candidate for replacement. And so we must continue here and find the page that's less recently used, let's say, than this one. However, before we move on, we will put now the reference bit of page 3 to 0. We clear its reference bit, more precisely. And that, of course, means that we will not give it a second chance. Next time we see it, we will not skip it again. Okay, now we continue and we move now, of course, to a frame whose occupying page 4, is not pinned, nor has the reference bit on, as you can see here. So we now have a good, let's say, acceptable candidate for replacement. And this is what we do. We replace, so page 4 was not dirty, so we just throw it away. We forget about it. We don't need to write it back to disk. The copy that we have already on disk, the primary copy that is on disk, is the exact copy of what we have in main memory here. And so we place page 7 in the frame 4. We set page 7. We set it as pinned. We indicate that it is currently in use by one operation, and we also set the reference bit, and then we advance the clock. And of course, we return the pointer to the requester of that page, indicating here is the page that you have requested. So this will be, let's say, the situation of the clock policy after dealing with the request for page 7. Okay, and if you want to know how this looks like in terms of code, here is, for instance, a small snapshot of code from the Postgres database, which is, of course, a free and open source database that anyone can use, anyone can modify, adapt according to their needs. And I would say it is not more complicated than it sounds, than we discussed about. You can see here a case discussion in which, depending on the dirty bit and so on, we follow the policy that we saw through an example before. And depending, of course, on the pin count. Okay, so here is now a first, another quick quiz for this section. So we have 4 buffer pages, 4 buffer frames, organized, let's say, vertically here. And each column in this matrix gives the state of the buffer at a given time step. So each column corresponds to one time step, or one tick of the clock, if you want. And in this matrix, we will only illustrate what changes. And we see here, for instance, so we have 4 buffer pages, and we see the access pattern, the order in which pages have been requested. So we have pages A, B, C, D, E, F, G, and only 4 buffer frames in which we can place them. This is the access pattern. And of course, we start with requesting A, then B, then C, then D. And of course, this will be the first pages that will occupy the 4 frames of our buffer. Since, of course, let's say initially the buffer is empty. And so at time 1, we place A in the top frame, at time 2, B, time 3, C, time 4, D. Now, of course, we have to continue this access pattern, and our job will be, let's say, to detail what happens for the remaining 10 steps if we follow the recently used policy. And in particular, we have to compute the hit rate. How many times out of the 14 requests of pages we had the page already in main memory, following the least recently used policy. So this is the kind of answer that is expected here, and let's discuss it a bit together. And here, whenever you see a star, that indicates a cache hit. The requested page is already in the buffer. Whenever you see a new letter in blue here, it means that the page that was occupying the slot has been replaced by the new one, and of course we follow in the replacement decisions. We follow, let's say, the least recently used policy as indicated here. And so let's look at the access pattern. So once again, each line, of course, corresponds to one frame. So the top line is frame 1, second line is frame 2, frame 3, frame 4 as well. And each column corresponds to one time stamp. Let me pick also the pointer. Okay, so the first four requests have been, of course, cache misses, because initially the cache was empty, and we placed page A in frame 1, page B in frame 2, page C in frame 3, and page D in frame 4. Then, so for now we have 0 cache hits. We have only misses. Then page A is requested again, and we have it in the buffer. So we have a first cache hit indicated by the star here. Then a request for page F arrives. Page F is not in the buffer, of course. We need to find a candidate for replacement. We need to kick out some existing page from the buffer in order to make space for F. And the least recently used, of course, will decide upon B. B is the least recently used page here. A obviously is the most recently used. We just requested it here. And obviously B was requested at step 2, C was requested at step 3, D was requested at step 4. And therefore B will be replaced here by F. And of course, at this stage, we have another cache miss. F was not in main memory. And so for now, we are still at 1 hit. Then we are here. A is requested again, second cache hit. So 2 cache hits for now. D is requested, and we have it, 3 cache hits. G is requested, and we don't have it. And if you trace back the operations, obviously C will be the least recently used page, and therefore in buffer in the frame 3 we will now place G instead of C. We continue with D, which is a cache hit. Of course, we still have D in the buffer, so 4th cache hit. Then we get G is requested, and we also have it in the buffer, so 5th hit. Then E is requested, and we don't have it. And once again, if you trace back all the operations that we have done, you will see that B was the least recently used page. Sorry, F was the least recently used page here, and so we will replace F with E in the frame 2. Then D is requested again, and we have it. This is the 6th cache hit. And finally, F is requested, and we don't have it anymore in the buffer. And here A will be the least recently used page. It has been used last here at step 7, and therefore we will replace page A with page F in the frame 1. And overall, we have a hit rate of 6 out of 14 requests. Okay, so now we have seen the least recently used and its simplified version, the clock policy. And we have also said that, let's say they are intuitive, they follow an intuitive logic, and conceptually least recently used is simple, not necessarily enforcing it. Well, the clock policy is also easy to enforce. And now, of course, the obvious question is: do we need to look further? Are least recently used and clock the best idea overall in any given circumstances, or do we need to look further or elsewhere for other policies? And well, what we can definitely say is that they work very well when we have this temporal locality aspect, when basically some pages are much more likely than others to be accessed in a short lapse of time. Remember, of course, that least recently used can be quite costlier than the clock policy, even if, of course, they have the same underlying idea. But we will see that there are situations when both least recently used and clock perform really badly. And this is the situations when we need to scan repeatedly, for instance, a big file. Let's see this situation through an example first of all. Repeated scans, once again, repeated sequential scans of a large file. Large meaning, of course, larger here than the buffer zone. So let's look at such an example. So we have a file worth of 7 pages of data, and we have just 6 frames in the buffer zone. And we need to read in succession, let's say 1 page at a time, starting with page 2, page 1, then page 2, and so on, this file. And we need to do it not just once, but several times. And by the way, this is quite a common situation in reality. For instance, when we do nested loop joins, remember that in nested loop joins, we were scanning repeatedly the relation that was the inner branch of the join, right? This may be the situation here. So let's see what happens following, of course, the least recently used policy, but a similar phenomenon will be observed with the clock policy. And we'll keep count of the requests on one hand and of the cache hits, so attempts or requests and cache hits. And of course, the misses will be the difference between the number of attempts and the number of hits. Okay, so the first page, page 1 is requested. For now, we start with an empty buffer, of course, so we don't have it. So we have 1 attempt, 0 cache hits. Page 2 is requested, 2 attempts, still 0 cache hits. So you can see how this goes. Initially, we only have attempts, but no cache hits. So far, they are, let's say, unavoidable cache misses. Now, this is where complications appear. We did not finish our first scan, sequential scan of this file. We have to access now page 7. Now the buffer, of course, is full, and we need a candidate for replacement. And of course, since we are using all LRU, the candidate for replacement will be page 1. So we will place page 7 in the first frame at the place of page 1. For now, we still have 0 cache hits, of course. Okay, and now we go back. We have to do a second sequential scan of our file, starting with page 1. Page 1, obviously, let's see what happened here. Page 1 is no longer in main memory. The buffer zone is full. We need a candidate for replacement, and that, of course, now with LRU will be page 2. So page 2 will be replaced now by page 1. We move to page 2, and for now, of course, we are at 8 attempts and still 0 cache hits. Now we need to read again page 2. Well, we are very unlucky, of course. We just kicked it out of the buffer zone, and we need to bring it back at the place of page 3. Now we just immediately after that, we need page 3, and therefore we need to bring it back at the place of page 4 and so on. And you can see how this goes. The number of attempts increases, but the cache hits remain at 0. And this is a phenomenon that has a specific name. It is called sequential flooding. So here, after 2 scans basically of the file, the hit rate remains at 0%, even if, of course, the buffer zone is almost as big as the data, right? And in reality, we are rarely that lucky, of course. The ratio data buffer size is much smaller, and still we'll have a 0% hit rate, and it would go like that for many times, not just 2 sequential scans, but 10 sequential scans and so on. The cache hit rate will remain at 0%. So this is what is called the sequential flooding, and I will let you, let's say, picture the name. Basically, it's a name indicating that with sequential scans, basically we have this flooding effect, in which basically all attempts resort to an input to a request to disk, which is of course catastrophic in the end. So obviously now the question is, with sequential scans, how could we do better? Obviously by changing the policy, and in that case, what if we use, instead of least recently used, most recently used? And once again, the name of this policy is self-explanatory. Now we will replace the page that was used most recently instead of least recently. So let's see what will be the behavior under this new policy for our sequential scans. And let's start here. So we are in the middle or in the process of the first sequential scan. We have just read pages 1 to 6. We have placed them into the buffer zone. And for now, we have unavoidably just 6 attempts and 0 cache hits. And now page 7 is requested. And now we have to pick the candidate for replacement. And with MRU, it will be, of course, page 6. Page 6 is the one that was most recently used. So now, of course, we'll place page 7 at the place of page 6. And our first sequential scan of this file is finished. We move now to the second sequential scan. Page 1 is read, and now we have finally a cache hit. Page 1 was already in main memory, so no longer needing a request from disk. Page 2 as well. Page 3, page 4, page 5, page, and we arrive, of course, and so at this point we have 5 hits, 12 attempts. So the number of misses, of course, is 12 minus 5. We arrive at page 6, which is not in main memory, so we have to pick now a replacement for it. And obviously page 5 is the most recently used. So we'll place page 6 instead of page 5. Page 7 is in main memory, so we have another cache hit. So you see how this goes. Page 2, page 3, page 4 is also a hit. Page 5 is now a miss, and we'll replace page 4 by page 5. And on like that, of course, as many scans as necessary, let's say. And so we can generalize this into a formula which will look like this. If we have B buffers and a file which is n larger or much larger than B pages in size, the first n attempts will lead to 0 hits, and then the next n attempts will lead to B minus 1 hits, corresponding to pages 1 through B minus 1, exactly what happened in our example. Then the next n attempts, B minus 1 hits, corresponding to pages n through B minus 1, and so on. And let's say at the limit for going, let's say, for doing many sequential scans, the hit rate will roughly be this, B minus 1. So let's say size of the buffer, more or less, divided by n, size of the data, which is obviously a reasonable hit rate. Obviously a reasonable hit rate because there are no miracles, let's say, we can do here. We have a buffer zone which is much smaller than the data itself. Okay, so if we talk about sequential scans, an improvement that is quite obvious, let's say, is to prefetch pages. Why read just one page at a time when we know very well that we'll then need to read the next one immediately after. So after page 1, we'll know that comes, page 2 will be requested, and so on. And so obviously we can ask for contiguous chunks of pages. And this, of course, helps by amortizing, let's say, the input-output overhead. So to wrap up what we have seen so far regarding replacement policies, what you should remember here is that least recently used is a good policy when we have this temporal locality. When we are in scenarios in which certain pages are much hotter, let's say, than others, much more likely to be accessed in the near future than others. But it's not so good, or we could even say catastrophic, in fact, um, in other scenarios. For instance, when we do repeated sequential scans of the same file. Most recently used is, of course, not designed for temporal locality. It goes in the opposite direction, obviously. It would be catastrophic when we use it in a scenario where some pages are much hotter than others, much more likely to be used in the near future than others. But it works better than least recently used. Uh, I would say as good as possible, in fact, considering the hit rate analysis that we just had on the previous slide for repeated sequential scans. For instance, for certain join operations like block nested loop joins. So in practice, uh, in a database management system, uh, obviously the system can provide, let's say, hints to the buffer manager. Hints like I am doing a sequential scan on behalf of a nested loop join, for instance. And obviously such hints will allow the buffer manager to be adaptive, to more or less follow let's say, the appropriate replacement policy depending on what is happening with the data. Um, there are, of course, fancier, more complex policies, for instance, based on stochastic probabilistic principles, like 2Q or least recently used 2ARC and so on. There are, for instance, general purpose pages like Wikipedia that you can consult for that, for replacement policies in general, not only designed for the cache of a database management system, but for caching mechanisms in general. And finally, for this discussion, it's oftentimes a good idea to rely on hybrid policies, a mix of policies, if you want, depending once again on the situation at hand, and having mechanisms that are adaptive in a way in order to choose the right policy at the right moment, depending on what is happening with the data. For instance, in PostgreSQL, for instance, currently uses clock. And for instance, that corresponds to the little piece of code that we just saw together. But there are other options that can be used as well. Okay, now it's time for another quick quiz regarding this discussion. True or false, does sequential flooding spoil the cache hit rate regardless of the replacement policy? And true or false, most recently used dominates least recently used in all cases. Okay, false and false. Oh, we don't have the answer for that as well. So I would say the answer for the first question is true. Sequential flooding spoils the hit rate regardless of the replacement policy. Even with most recently used, we saw that the hit rate will not be great, will be basically size of the buffer divided by size of the data. And you can imagine that there are situations in which the data is much larger than the size of the buffer. Obviously, unavoidable, I would say, that such a hit rate would be unavoidable for sequential scans, but still, it's definitely not a good hit rate. We may imagine other situations when we don't have to do sequential scans, where the hit rate may be close to 1. But here with sequential flooding, with sequential scans of a large file, the hit rate will be very low regardless of the replacement policy. So here the answer is true. And obviously, for the second question, the answer is false because we don't have one policy, whether it is least or most, that dominates the other. There are situations in which one works better than the other and situations where the opposite happens. Okay, another quick quiz. For least recently used, the score each of the access patterns, sorry, for least recently used, score each of the access patterns as good or bad with respect to cache hit rate. Is least recently used good or bad for repeatedly scans of a file bigger than the buffer pool? Is it good or bad for repeatedly scans of a file smaller than the buffer pool? Good or bad for making independent random accesses to a file larger than the buffer pool, and good or bad for making random accesses to a file smaller than the buffer pool. What do you think? So basically you have to give me in order uh, a list of good, bad values. Okay, so I see big and then all good. Bad, sorry, bad and then all good. So obviously, for A, that was the issue of least recently used, bad at repeated scan of a file that is bigger than the buffer zone. If the file is smaller than the buffer zone, then all is good because we just place the file in the buffer and we will access it basically only with cache hits. So definitely good for that, obviously. C is obviously the scenario in which the least recently used policy works best. Random accesses to a file that is large. Random accesses, of course, here is more or less a synonym for temporal locality. The assumption that some pages will be hotter than others, will be most likely accessed in the near future than others. And then again, if the file is smaller than the buffer pool, obviously, regardless of the policy, all is good. So bad, good, good, and good. Okay, the same question now for most recently used. And the situations A, B, C, D are the same as before. So what do you think now? Good, good, bad, good. Okay, so for A, it's debatable, I would say. We could say that most recently used is good at doing repeated scans of a file that is bigger than the buffer pool, but actually we should make it a bit more precise. It's better than least recently used, but definitely I would say we cannot qualify it as good. It still remains bad, more or less, as we discussed before. And of course, we can also add that regardless of the policy, unavoidably the hit rate will be low when we do repeated scans of a file that is bigger or much bigger than the buffer. So here we could say better than least recently used, but still bad. Obviously good for B, any policy would be fine. Obviously bad for C. It's not designed for that, and it goes against the principle that uh, uh, we, in situations where we have pages that are much hotter than others, we should keep them in the buffer instead of replacing them. And obviously for D, it is good because once again, any policy would be good here since the file is much smaller than the buffer pool. Okay, so here bad, good, bad, and good. Okay, now let's say reaching a conclusion to this section, um, you sorry. Um, a final question that we should clarify here is why does the database management system need to implement, let's say, its own cache mechanisms? Why not rely on the ones of the operating system? And of course, you can imagine that the operating system has a very similar, let's say, intermediary module between the disk and the main memory, between the disk and the RAM space. A module that also implements, of course, cache policies. When we use the computer, of course, we need to bring data at all times from disk into main memory in order to use it. And by now, for instance, working on the practical assignment 1, you are aware that we have much less main memory than disk space. So the same kind of cache policies are necessary also at the operating system level. And so the question here would be, why do we have to re-implement in a way such cache policies if the file system and the operating system already have them? And there are several reasons for that. First of all, portability. Because with different file systems, we may end up having different behaviors. And this is, of course, something we want to avoid in a database management system, which should have the same behavior regardless of the file system, regardless of the operating system. There are various operating system limitations. For instance, a database file may need to span multiple disks, or this is not possible, let's say, within the scope of a file system. We will also see that there are situations in which the database management system needs, let's say, to have direct impact, let's say, to have the ability to force pages to disk. For instance, when we recover, when we are in the process of recovering from a crash. And so this is why we cannot go through the operating system as an intermediary, because the database management system needs to have direct, let's say, ability to force pages to disk in certain situations. There are limitations as well, because the database management system can predict its own page reference patterns. We may be in the process of, in the middle of a nested loop join, and therefore we know that we will scan repeatedly the inner relation. The operating system doesn't understand that, of course. Or we may be in the process of computing a count over a relation just by looking at the leaf level of a B plus tree. So scanning sequentially the leaves of a B plus tree. The operating system will not understand what is going on. And understanding basically how the data is in use at a given moment, for instance, in query execution, will affect, of course, both the page replacement decisions and the prefetching decisions that we may want to take. And this is why basically the DBMS needs to have its own mechanisms for basically this cache level between the disk and the main memory. Okay, so summing up here, what you should remember is that the buffer manager provides a level of indirection, mapping disk pages to let's say, main memory frames, to RAM addresses. It ensures that each requested page is pinned in main memory in order to indicate it is in use. And also, it is very important that such pages will then be unpinned by the requester of the page. And so this is, of course, the pinned information is very important for the replacement decisions, because we cannot replace a page that is currently in use, is indicated as currently in use. And one of the main, let's say, objectives of the buffer manager will be, of course, to minimize cache misses, to minimize the probability that the page that is being requested by the levels above is not in main memory already at the moment of the request. And this is done by replacing pages that are most unlikely to be requested in the near future, and by prefetching pages that are likely to be requested in the near future. So replacing and prefetching will be, let's say, the key let's say, aspects of the buffer manager, the key decisions that the buffer manager needs to take. So what you should remember here, first of all, how we keep track of everything needed, for instance, for page replacement. The pin counts, the dirty bits, when do we set or unset them, who is responsible for that as well. And of course, the common replacement policies that we discussed, least recently used, most recently used, and clock as a simplification of least recently used. And understand them in order to, for instance, be able to run each of them by hand on a little example. And also, you should understand situations like sequential flooding and how they are handled more or less in a good way, let's say, um, by policies such as least recently used or most recently used. Okay, so with this, we finished this chapter of our discussion, and we will move to the next set of slides on concurrency control. There is also a question, why is the dirty page set by the requester instead of the buffer manager? Because basically the requester knows if the page has been modified or not. It's not the role of the buffer manager to infer somehow that the page was modified. Okay, so let me now move to the next set of slides. Okay, so now it's 3:49 p.m., but let's take the break now so that we don't interrupt the discussion later on. So let's take a break of 10 minutes until 4 p.m. and then we will continue the class with the discussion on transactions and concurrency control. Okay, so break of 10 minutes, and during the break, of course, feel free to ask questions as well.